Welcome to another informative video brought to you by Autruo. The last time we started off by setting up the simulating environment. These machines are conveyor and palleting machine respectively. Finally, we ended off with the placement of censoring device as per program requirement. In this series, we will be writing some set of programs to control this machine in synchronization using the IEC-approved programming languages. Stay tuned. Now, I will be opening my programming software. And in this case, we are using the TIA portal application. Again, there is need for us to add additional input and output modules. Now, we want to implement some added features that will make some indicators lamp to blink at intervals. You know those lamps that blinked on some factory workstation when there are issues with the process. So I will click my CPU here and I will click System and Clock Memory. Will enable the use of a clock memory byte. After enabling, I will change our bit from 0 to 10. With this, we will have some global memory to use during program writing. So basically, we will be considering 2.5 Hz clock. Don't worry, you will get to understand what we want to do in just a moment. Now back to the program writing. We will be starting with creating a new function block called start and stop button. Here is where the starting and stop conditions will be written. Again, we'll like to create new I/O tags. These will be called program tags. We will be starting with the start button. The data type of the start button is a Boolean type. And the address we are considering is I0.2. Of course, the comments will be button used to start the conveyor and palletizer system. The next one will be the stop button. The bit address will be I0.3. And the comments will be to stop the whole machine. For the emergency button, the bit address will be I0.4. Comments will be to stop the whole system during emergency situations. Finally, we will be creating an internal coil that will be used extensively in our program. This time, the bit address will be M0.0, and comments will be an internal memory coil that will be used to start the network. So in the start and stop block, we will write our start button parallel with or machine sys run and stop button and emergency button equal to machine sys run. Again, the equal means the result of the program. The language we just use here is called statement list, or STL as it is fondly called. We will create another block. We will call this block machine lighting conditions. Here is where we will be programming how the stack light will behave under certain conditions. Here machine sys run, which is a normally open condition, is parallel with green light. Again, just like I said earlier, this machine sys run is going to be used extensively. The plan is to design this conveyor and palleting machine in such a way that all networks within this program will not be active unless the start button is triggered. Now back to the programming. The start button is also parallel to the machine sys run. The yellow light is parallel to not true and normally open contact of the emergency stop button. A little glance at what this means. The not mean when the network is active, the output will not be active, and when the network is not active, the output of the not will be active. Now looking at what we want to achieve here. We want a situation whereby, when the start button is not triggered, we want the yellow stack light to come on. Of course, we know that the yellow light sometime means the machine is on standby mode. Again, the stop button is also in series with this network. By so doing, the stop button will also be active too. The next programming lines will also be connected to the NOT. Now, if you can recall earlier on, we enable the system and clock memory. In our case here, these features make the output coil blink at intervals. In this case, we will be using 2.5 Hz, which is M10.2. This contact will be in series with the normally close contact of the stop, and the result of the coil will be red light. With these, the aim is to have a red stack light that blinks when the emergency button is triggered. We will drag these two FB to OB1 for program calling. We will now download the written program to our PLC sim. Also, we will need to drag the I/O to the respective bit address in the simulating software. In our case here, we are using factory I/O.
Perfect, Andrea. Most especially the blinking output coils. These will easily catch the awareness of the operator and those around the equipment at that point in time. Again, these lights are bystanders when it comes to machine design. Equipment manufacturers design their machines in such a way that the status of the machine can be known at distance. This will sometimes lead to increase in productivity because decisions can be made at distance. And the NOT manipulation is also handy too, as seen in what you wrote. Which means when the start button is not triggered, the yellow light comes on, and the way you manipulated the red light is top-notch. Hence there will be a difference in when the machine stops as a result of when the stop button is triggered to when it stops during emergency situations. Back to you, Andrea.
Now by default, the machine is on standby as indicated by the yellow light. Now when I triggered the buttons, the stack light conditions change accordingly.
Perfect, Andrea. So this FB is programmed using one of the text programming languages under IEC 61131-3 programming languages. Perfect, Andrea.
Yes, Hendrik. So we will create another FB. This FB will be used to control the conveyor that will move the pallet from the emitter to the Turnstar table. The machine sys-run coil will be connected in series with the emitter. With these, the aim is to control pallet emitting via the start button. Another network will be created. Again, the machine sys-run will be connected to the three conveyors. Again, I will drag the FB to OB1 for program calling. Then we'll download the written program to the PLC sim. Now, when the start button was triggered, the conveyors move accordingly. Let's implement a control. What we want is for the conveyor to stop during pallet backup. So in the next network, we will incorporate this sensor with a timer. We'll set it to 50 seconds, which means the conveyor should stop after 50 seconds of inactivity. Let's download this to our PLC sim.
Perfect. This is necessary because the frequent start and stop of electric motors will have a negative effect on the motors and some other connecting devices. Looking at this historical data, as you can see from the first graph, this motor starts very often and from the data gotten. This has a lesser lifespan as compared to the motor that start and stop less often. From this data, this motor has a longer life as compared to the other motor. Again, the contactors will also be affected because of the frequent energizing of the contactors' coils. Back to you, Andrea.
As you can see, when I create a delay here, The timer will count down, and after some time, the motor that is driving the contactors will stop.
Perfect, Andrea. Most like the reason why some motors stop after some time of inactivities.
Now the next thing is the Turnstar programming. This block will be programmed using function block diagram, which is sometimes called FBD. Here we'll be using a bit operation which is called flip-flop. Let's quickly look at how these blocks work. When the set is active, the output coil will be active. However, when the R is active, which is also called reset, the coil will become inactive. So in our case here, we intend to control the turntable displacement. Now, this is what we will do. This approach sensor will be tagged to the set input, and the output of the network will be tagged to the motor that rotates the Turnstar. We'll drag the block to the OB1, and I will also drag the I/O to the respective addresses in the factory I/O drivers. Now when the first pallet cut the approach sensor, the Turnstar table will turn to receive the pallet. Now that the table has turned to receive the pallet, the next thing is to write the condition that will put the Turnstar table back to its initial position. The backward limit sensor, which is the sensor that is at the rear end of the Turnstar table. This sensor will be connected in parallel with the backward limit memories. The backward limit memory is a global memory. So again you understand the reason why the blinking bit was set as 10, because we'll be using a lot of these global memories. Now let's put it in perspective, since we are using 10. Which means that we will be having 80-bit address to play with it, which should be enough for this programming. Now back to the programming. This OR condition will be in series with this AND condition. And in this case, we will be using this sensor, which is known as the turnback sensor. And all these conditions will equal to the backward limit memories. The backward limit memories will be tagged to the rest of the flip-flop bit logic operation. This means that when the pallet roll in up to the backward limit sensor, the turntable turns back to its initial. The table will remain at its initial unless the pallets break this sensor, which is known as turnback sensor.
So in other words, Andrea, when the pallet approaches this sensor here, the Turnstar table will turn 90 degrees to receive the pallet. And when the pallet rolls in, the table turns to its initial position. This is great, Andrea.
Now, the pallet will need to roll inward. Also, we will be using the OR operations. Now we will be considering this sensor, which is known as the Turnstar sensor. This will be in parallel with the backward roll-in conveyor. That is to roll the pallet inward. This OR bit operation will be in series with the AND bit operation. That is in series with the normally open contact of the Turnstar at 90 degrees and in series with the normally close contact of the backward limit sensor. And all this is equal to the backward roll-in conveyor. To make it sync further, when the pallet approaches this sensor, that is the Turnstar sensor. And when the table is turned at 90 degrees, then the backward roll-in conveyor will be active. Now, when the pallet reaches the backward limit sensor, the backward roll-in conveyor will stop, and because this sensor is also used at this flip-flop, and the tables will also turn back to its initials. Now let's download the written program to our PLC sim. And will also tagged to the I/O of the factory I/O drivers. And let's see.
Perfect, Andrea. Perfect.
This is what they called robotics. Again, all these things are series of instructions working together.
The next thing is to write some set of instructions that will be used to roll out the conveyors. In this case, we will be using the AND-bit logic operations. In the AND-bit logic operations, the normally open contact of the backward limit sensor will be connected in series with the normally open contact of Turnstar at 0 degrees. And it will be further in series with another flip-flop. This will be connected to the set of the flip-flop, while the turnback sensor will be connected to the reset bit logic of the flip-flop, and the other result of this programming will be connected to the forward rollout of the conveyor. So this is how it is going to work. We want the forward conveyor that will roll out the pallet to be active when the pallet is detected by the sensor, and the Turnstar is at its initial position. Then it should stop rotating as soon as the pallet is detected by the turnback sensor. Now we'll download this to the PLC sim. We will also tag the I/O to the factory I/O drivers. As you can see, the pallet is rolling out. Now we will be putting some contact in the empty conveyor at the in-feed block. We'll create a buffer time here. We will add another flip-flop from the bit logic operation. The set of the flop will be tagged to the backward limit sensor, while the reset will be tagged to the turnback sensor. We will create a buffer time which is global memories. The normally close contact of these global memories will be tagged to the conveyor rung. Again, we also intend to control how the pallet will be emitted. So we'll put one of the conveyor contacts at the emitter rung. Now when the conveyor stops, the pallet will stop emitting as well.
I see. The in-feed conveyor becomes active as soon as the forward conveyor rotates. Perfect. Those additional contacts solve the problem.
So when the conveyor stops, the emitter also stops emitting pallet as well. Perfect, Andrea.
Now the last set of program writing for this series is the conveyor that will take the pallet to the palletizer. We will be adding a or bit logic operation. In the or bit logic operation, we will tag it to this sensor called empty to palletizer sensor, parallel to pal conveyor to palletizer 1. The or bit logic will further be connected to an bit logic operation. In this and bit logic operation, we will be having 3 normally closed contacts. One of the contacts will be used to sense the back limit sensor at the palletizer elevator, while another will be used to sense the pallet at the front elevator, and the last one will be connected to the local memories of the backup sensor. Here we'll be adding a timer. In the timer, the backup sensor will be tagged to the timer input, while the output of the timer will be tagged to the local memories. The output of all this instruction will be connected to all the 3 conveyor motors simultaneously. We will download this program to our simulator and the I/O tag will be connected to the drivers of the factory I/O.
Perfect, Andrea. Everything is working as described and in synchronization.
Perfect, Andrea. Nice piece of programming.
In the next series, I will be writing some set of program instructions that will be used to control the palletizer machine in synchronization with the conveyor system. Hope you have learned something new today. See you in the next one.